topography. In the previous session, we have seen how to perform sampling of an analog signal, as well as we have seen sampling theorem. In this session, we will be looking at one example on sampling theorem. In previous session, we have already discussed how to obtain discrete time signal from the analog signal. What is sampling frequency, that is capital Fs. What is sampling period, denoted by capital T. How to identify that sampling frequency from this analog signal frequency, capital F. In sampling theorem, I have seen that sampling frequency should be selected greater than twice of maximum frequency to reconstruct analog signal from its discrete time version properly. And for reconstructing the discrete time signal from the analog signal, we can use interpolation function. So all these topics we have already discussed in the previous session. So let's look at one of the example on sampling theorem. So here you can see the example has been given. Here we have to convert the given analog signal xa of t. So we have to convert this analog signal xa of t, which is given as 3 cos 50 pi t plus 10 sin 300 pi t minus cos 100 pi t. Okay. So you have to identify the Nyquist rate for this signal, and we'll try to extend this problem. We'll try to identify sampling frequency is Fs for this given analog signal, right? As well as we'll try to identify the discrete time signal, that is x of n. Okay, from this analog signal x of t. So before solving this problem, what we have seen in the previous session, we have taken an analog signal, that is x of t, as a cos 2 pi ft plus theta. So we have taken it as an analog signal, and we have tried to convert it into discrete time signal. So here this we are taken as what? An analog signal xa of t is equals to a cos 2 pi ft plus theta, and its discrete time version is represented as x of n, which is we have identified from xa of t simply by replacing small t with small n, capital T. So this we have rewritten as a cos 2 pi f. Here we have replaced the small t with small n, capital T plus theta. So here we have already seen this capital F was the frequency for analog signal, and it should be finite. It will be minus infinity less than capital F less than infinity. So this analog signal frequency, capital F, should be between this range. Okay? So again, let's say this capital T is called as what? Sampling period, or the sampling interval. successive samples. This capital T is nothing but 1 upon Fs. And this Fs is the sampling frequency. So this capital T can be replaced with 1 upon Fs, right? Plus theta. Okay. So again, this can be written as A cos 2 pi capital F upon Fs and plus theta, right? So this will be equals to what? A cos 2 pi. We have replaced this capital F upon Fs with small f, small fn plus theta. This was our final discrete time signal. And the frequency range for this small f, that is frequency of this discrete time signal x of n, is between -1/2 less than small f less than 1/2. Okay, and here we have already seen this -1/2 less than small f is nothing but your f upon fs, f upon fs less than 1/2. So these we have seen in the previous session, and as per sampling theorem, okay, to reconstruct this analog signal x of t from its discrete version x of n, we should select sampling frequency fs sufficiently high, that is fs should be selected as greater than twice of maximum frequency. Okay. So in this case there was only one frequency component capital F, so it will be greater than twice of f. Okay. As per sampling theorem, this sampling frequency of f should be greater than twice of maximum frequency. We also seen is if you are selecting sampling frequency is equals to twice of maximum frequency. Okay. This is called as what? Nyquist rate, denoted as Fn. Correct. And this is equivalent to what? Twice of bandwidth. Right. These things we have already seen in the previous session. So in this example, we have to identify the Nyquist rate. To identify the Nyquist rate, we have to identify the sampling frequency, and we have to identify the discrete time signal, okay, x of n. So that means we will try to identify this x of n, right? We'll try to identify the Nyquist rate fn, as well as we will try to identify the sampling frequency, that is fs. So now let's look at in sampling theorem. We have also seen this analog signal, okay, that is x of n can be x of t can be reconstructed from the x of n by using the interpolation function, that is g of t, which is nothing but what we have there, sine 2 pi bt upon 2 pi bt. Okay, so how to use this interpolation function for reconstruction of analog signal from the discrete time signal, okay, that has been stated in the sampling theorem. Okay, we have seen it in previous session, right? So that means to reconstruct the analog signal from discrete time signal, we should select sampling frequency sufficiently high, greater than twice of maximum frequency. Okay, so now let's solve this problem. Here we are extending this problem. We will try to identify the Nyquist rate, okay, that is Fn, as well as we will try to identify the sampling frequency, and as well as we will try to identify the discrete times. That is x of n, from the given x of t. Now solve this. So solution. So the given analog signal. Solution will be so given analog signal x of t is equals to 3 cos 50 by t plus 10 sin 300 by t minus cos of 100 by t. So if you compare this given analog signal x of t with what we have considered in this previous slide, so this x of t is equals to, we have considered a cos 2 pi f t plus theta. So in place of a cos 2 pi f t, in place of a cos 2 pi f t plus theta, so this we have considered in the previous slide as an analog signal. So we're trying to solve this example. Here select n. So here we are trying to identify the Nyquist rate, that is Fm, as well as we will try to identify the sampling frequency as Fs. We would like to identify the discrete time signal S of n. So now let's solve this example. We'll try to solve this problem. So here the given analog signal x of t is equals to, what is here, 3 cos 50 by t plus 10 sin 300 by t minus cos 100 by t. So if you compare this analog signal with what we have considered in previous slide, okay, so we have considered this x of t as analog signal and we have taken it as a cos 2 pi f t plus theta, right? So what we have taken it as, we have taken x of t in previous slide as a cos 2 pi f t plus theta, right? So if you compare this given x of t with what we have taken, right? So basically the given x of t comprises multiple components of frequencies, right? So in place of a, here 3 is there. In place of 2 pi ft, it is 50 pi t, okay, that means 2f is equals to 50 here, okay, that means f is equals to 25, right? Capital F is equals to 25. Theta is not specified here, right? But this term, that is a cos 2 pi ft, in place of this a cos 2 pi ft, first term contains 3 cos 50 pi t plus 10 sin 300 pi t minus uh, cos 100 pi t. So basically there are instead of single term there are three different terms. That means first term is 3 cos 50 pi t, the second term is 10 sin 300 pi t, and third term is minus cos 100 pi t. Right. So if you compare with this what we have considered, so in place of a 3 is there, in place of 2 2f, in first term 50 is there, right? In second term in place of a 10 is there, right? In place of 2f 300 is there, and in place of a in third term minus 1 is there, right? Minus 1, and in place of 2f 100 is there. So this given analog signal contains three frequency components. Okay, so the first frequency component, that is f1, is nothing but, because in place of 2f there is 50, so first frequency component is nothing but 25 hertz, right? Similarly, second frequency component f2 is 150 hertz, and third frequency component is 50 hertz. So how we identified it? These frequency components, we identified it from the given analog signal, because in place of 2f 50 is there, so that means f is nothing but 25, that is 50 divided by 2. In second term in place of 2f 300 is there, so f is equals to 300 by 2, so it will be 150 hertz, right? And similarly in place of 2f here 100 is there, so that means capital F is equals to 100 by 2, that will be 50 hertz. So this analog signal contains three frequency components. Okay, that is f1 is equals to 25 hertz, f2 is equals to 150 hertz, and f3 is equals to 50 hertz. So to identify the sampling frequency and Nyquist rate, initially we should identify the maximum frequency. So out of these three frequency component f1, f2 and f3, which one is the maximum? So f2 is the maximum. Okay, so therefore in this case this maximum frequency component of the given analog signal is nothing but f2, which will be equals to 150 hertz. Okay. So therefore the what Nyquist rate Fn is equals to twice of maximum frequency. So that means it will be simply 2 multiplied by 150, so it will be 300 hertz. So this will be what the Nyquist rate Fn. Now next we'll try to identify the sampling frequency. So the sampling frequency should be greater than twice of maximum frequency. So again this f max can be replaced with 150 hertz, so that means this sampling frequency should be greater than 300 hertz. Okay. So you can select any sampling frequency with value, or any frequency with value greater than 300 hertz as a sampling frequency. So I can consider here the sampling frequency, just for examples, fs is equals to, for example, 900 hertz. So I can take this 900 hertz as sampling frequency, because you can consider any frequency value greater than 300 hertz as sampling frequency. So I can take 900 hertz, or maybe 1000 hertz, that is 1 kilohertz, or maybe 2000 hertz, that is 2 kilohertz, or maybe 15,000 hertz, that is 50 kilohertz, right? So likewise, I can select any frequency greater than 300 hertz as sampling frequency. So what we identified here, we have identified Nyquist rate as 300 hertz, and we have taken sampling frequency as 900 hertz. And how we have identified this Nyquist rate and sampling frequency? By identifying the maximum frequency component of the given analog signal. Okay, so in the given analog signal, there were three frequency components: f1, f2, and f3. So first frequency component was 25 hertz, second was 150 hertz, and third was 50 hertz. Okay, out of this, we have taken maximum frequency component, that is f2, taken it as maximum frequency, so therefore 150 hertz was the maximum frequency component of the given analog signal, and from that we identified the Nyquist rate and the sampling frequency. Now let's try to identify the discrete time signal, that is x of n, okay, from the given analog signal. Okay, so how we have identified that discrete time signal? So that discrete time signal we have simply represented as x of n. Okay, and in previous slide we have taken this x of n as a cos 2 pi fn plus theta, but in our example theta is not there, so we can take it as simply what, a cos 2 pi small fn, okay, plus theta. So you cannot you can skip this theta, okay. And if you compare this with what we have, okay, so we have x of n is equals to a cos this 2 pi small f is nothing but capital F upon fs divided by n plus theta, right? So if you compare, okay, with the given analog signal, because this this x of t, okay, we have represented in discrete version like this x of n, but if I want to represent this given x of t, right, as x of n, so I can rewrite this equation as what? In case of a, there is 3, in place of cos function is there, right? And in place of 2f, okay, that is twice f, right? In place of 2f, 50 is there, right? So I can rewrite it as what, 2 pi 25 upon fs, okay, but fs I have considered as what, 900 hertz multiplied by small n, right? Plus similarly I can take it as what, 10 sine, again 2 pi, because I am simply rewriting this as 2 pi ft, okay. So capital F is nothing but here now 150, so 150 upon 900 multiplied by n, right? Minus cos, again 2 pi, okay, so 2 pi what, 50 upon 900 n, okay. So this is what discrete time version of the given analog signal. So more specifically we can specify this x of n, okay, so that is 3 cos, that is 2 pi fn, okay. So it is nothing but simply what, I can rewrite this signal as 50 upon 900 pi n plus 10 sine 300 900 by n minus cos 100 by 900 by n. Okay. And if you compute the values of this 500 by 900, sorry, 50 by 900, so I can replace these values here, right, and write my actual discrete time signal. Okay, so that means that I will write down the final equation. So this x of n, okay, that is 3 cos 50 by 900, 50 divided by 900 can be replaced with 0.05. Right? So I can write here. You can keep this equation as it is, or you can simply compute these values 0.55 by n plus 10 sine again 300 divided by 900. Okay, so again I can keep it as it is, or I can replace it with 0.33, right? So 10 sine 0.33 by n minus cos, again I can keep this 100 by 900 at it is, or I can replace it with 0.11. So cos 0.11 by n. Okay, so this is what final required discrete time signal. Okay, so in this example, what we have seen, where in this problem we have identified Nyquist rate. Okay, so we identified Nyquist rate Fn, which is nothing but 300 hertz. We have identified sampling frequency. We can select any frequency greater than 300 hertz as sampling frequency. So therefore we have taken sampling frequency as 900 hertz, right? And we identified the discrete time signal, that is x of n, from the given analog signal. So here x of n is simply identified cos 2 pi small fn, okay, plus theta, but this small f is nothing but capital F upon fs, and this capital F was the frequency of analog signal. So the frequencies available in the given analog signal, there were three frequency components, that is f1 25 hertz, f2 150 hertz, and f3 50 hertz. Okay, so this capital F upon Fs, so we have taken Fs sampling frequency as 900 hertz, so everywhere we have specified it as 900. So the given equation was 3 cos 50 pi t, that was analog signal components, okay, plus 10 sine 300 pi t minus cos 100 pi t. But in discrete time version, this a cos 2 pi fn were specified, but f is nothing but f upon fs, so we are rewritten it as 3 cos 2 pi f1 upon fs n plus 10 sine 2 pi f, in place of capital F, f2 is there, that is f2 upon fs were specified, multiplied by n minus cos 2 pi capital F3 upon fs, right, into n. And then we have multiplied this term, that is 2 multiplied by 25, that is 50 upon 900 will be there, 10 multiplied by 150, that is 300 upon 900, and 2 multiplied by 50 will be 100 upon 900. Okay, so finally we have computed these values and obtained the discrete time signal x of n. Okay, so likewise you can solve the given problems, okay, to identify the Nyquist rate, sampling frequency, and the discrete time signal x of n. Okay, so in this session we have seen how to identify the Nyquist rate from the given analog signal, that is Fn. Similarly, we are trying to identify the sampling frequency Fs and the discrete time signal x of n from the given analog signal x of t. In next session, we'll be looking at the remaining steps in analog to digital conversion process, that is quantization and coding. So we'll be looking at quantization of the discrete time signal, okay, in next session, as well as coding. So thank you for joining this session.